forecasting and simulation using at-risk in the DecisionTools suite. This is the third part, part 3 of our 3-part series, presented by Glen Justis of Experience on Demand. My name is Jameson Romeo Hall, and I'll be available to help answer technical questions by chat. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you're a part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the Q&A panel or the chat panel. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead products at risk and the DecisionTools suite. We invite you to sit back and relax and enjoy today's presentation. Glen, it's all yours.
Well, great. Well, Jameson, thank you very much. We appreciate the opportunity to present today and the great help that you've had, or provided, in helping us prepare for this. As Jameson mentioned, this is the third part of a three series of webcasts where we've covered business forecasting and analytics simulation using the Palisade DecisionTools suite. And we have focused predominantly on the at-risk tool, but have covered some of the other tools of the DecisionTools suite application set. As Jameson mentioned, my name is Glen Justis. I'm a partner at Experience on Demand. We're a small St. Louis-based consulting firm, and my background has been involved in not just serving utilities, but I've also done a fair amount of work in financial institutions, manufacturing, agricultural services, retail, as well as some social enterprise businesses, which have been interesting. The work I tend to specialize in are issues where strategy, economic analysis, and risk management intersect. I've had the opportunity to use the Palisade DecisionTools suite for quite a few years. Prior to working at Experience on Demand, I've held senior consulting positions at my own firm, Acclaim Strategies, as well as Deloitte & Touche, and a engineering management consulting firm called R.W. Beck. I have an MBA from Webster University in St. Louis, and as well as a degree in engineering. And so this background, I believe, has given me really a lot of great experiences to do advanced analytics, both in engineering and business and finance settings. A little bit more about Experience on Demand. Again, we're a St. Louis-based management consulting firm. Our mission is to help organizations develop and execute successful business strategies. And major practice areas for our firm include strategic planning and execution support, economic analysis, process design, supply chain optimization, as well as some of the software management consulting type areas of organizational development, leadership coaching, and training. We're in our 8th year. We've served approximately 150 organizations, and have had the good fortune of being honored as one of the best consulting firms in the region by Small Business Monthly. What I wanted to do in terms of an agenda today is provide a brief recap from webcasts 1 and 2 for those that weren't able to participate. We'll also, of course, cover our learning objectives. We'll jump into an overview of the case study. We'll talk a fair amount about how we've chosen to frame this particular problem, and then we'll cover the preliminary model. This is a bit of a work in progress. We are working with an actual case study with a live client. This client happens to be, and we'll of course cover this more a little bit later, but this client is a large municipal electric utility in Columbia, Missouri. Some of you may be familiar with Columbia Water and Light, but they're facing significant capital investment decisions, and we're working with them to explore how to apply at-risk and other modules of the DecisionTools suite in framing and analyzing those capital investment decisions. And what we'll be doing between now and about a month from now is further refining this model and then presenting it at the Palisade annual conference down in New Orleans in November. We'll, of course, share some observations, including some observations on some of my lessons learned and what I think are important considerations in introducing advanced simulation analytics into corporate settings, and then we'll talk about the next steps for the model in this particular analysis itself. Again, I wanted to provide a brief recap from Webcast 1 and 2. Webcast 1 was really focused on the basics of what does at-risk do, as well as the other modules of the DecisionTools suite. And in particular, we covered some of these concepts of really what are we talking about when we talk about advanced business analytics, and we distinguished between the different forms. First would be, in the way I like to describe it, is diagnostic or descriptive analytics, which is analyzing, slicing and dicing historical data, as well as data about data or metadata, to gain insight into past performance of an organization or a business problem. We then transition into predictive analytics and risk analytics, which I think are the key features and advantages of the DecisionTools suite. In other words, not only predicting future performance based on statistical analysis of trends, correlations, and relationships of key drivers, but also assessing potential performance and performance uncertainty with particular focus on rewarded and or organizationally sensitive risks. And then lastly, the advanced application of the DecisionTools suite really lends itself well to optimization, really finding what I would describe as the sweet spot for major decisions, using the power of data integration across the enterprise to analyze the business and identify unique value creation strategies and treating risks opportunistically. Some of the other things we covered in the Webcast 1 and 2 involve the rapid increase in investments in advanced analytics, and in this particular icon, we referenced the investments made by Ernst & Young, which were announced earlier this year on Advanced Global Analytics Center of Excellence, and this is similar to what other companies such as Deloitte & Touche and other major consulting firms have done. We also spent a good bit of time talking about this concept, which is referred to as Jensen's inequality. And the notion here is that the expected value of a probabilistic function does not equal the value of the function simply using the expected value of each of the key variables in that function. And a simple way to say that is it's almost necessary, not just interesting, but actually necessary, to apply Monte Carlo simulation to get high-quality answers when you have a nonlinear business function or business problem that you're trying to analyze. And then lastly, we talked about some of the key components of successful business initiatives, starting with good strategy, well executed, and then revolving around to continuous refinement and improvement of business strategy and operations. So some of the specific learning objectives of this webcast are, first of all, to frame value and risk issues in a capital investment decision context. That's really the core of what we're talking about today. We'll also cover some considerations and lessons learned in implementing simulation analytics in corporate settings. Those are the two main areas we want to cover today. So back to the overview of the case study, the capital investment context here is a large municipal water and electric utility, and the power plant is fueled by coal and natural gas. The coal units are over 50 years old, so they're older units. The oldest of the units runs reasonably well. The newer one runs better, but they still require extensive environmental and performance improvement investments. Those two coal plants are currently burning eastern coal as well as biomass, so this utility is introducing wood chips into their fuel mix for renewable energy goals. Again, they face major capital investment requirements, but also opportunities. And these investments revolve around environmental compliance. These are required if they want to keep generating with coal, and these environmental compliance requirements really stem from the new EPA regs as well as broader environmental compliance regulations that have continued to put greater and greater pressure on many industries, most notably electric utilities. These investments are also required, though, for ongoing unit reliability. So it's not just if they want to keep these plants available, but if they actually want to operate them in a reliable way to meet load and severe system conditions, they need to upgrade the facilities, but also for efficiency. These plants are not particularly efficient, and there are opportunities to improve the heat rates and other aspects of the efficiency of the plants. Some software issues, but that are also very important. Again, this is a municipal utility. It's basically a governmental entity, and the intersection of economics along with community values is very important, which is the case in almost all municipal utilities I've ever worked with. In this particular community, of course, values local control, like most electric utilities in a municipal setting do. So they value having their own generation and being in some degree of control of their own energy future. They also receive economic benefits of owning their own generation, which is important. And the community also values environmental stewardship and sustainability. Most communities, I would say all communities value that in this day and age. This community, which also is a college town, I would say values this in particular compared to some. More specifically, there's two coal-fired boilers, one gas-fired boiler, and then 3 steam turbine generators. And the size of these units, respectively, are 16, 22, and 35 megawatts. There's also a 12-megawatt gas-fired combustion turbine, which does not run very much, and we have not incorporated this unit in the mix, but we just wanted to describe this for sake of completeness. They also have 2 large baseload capacity contracts. These are basically power supply contracts they have with other surrounding utility organizations, and these are relatively large in size compared to their system. Again, 70 megawatts and 66 megawatts respectively. And the energy price within these contracts is relatively attractive. The energy price, as you'll see later, of the 70 megawatt contract is approximately $15 per unit, and the 66 megawatt capacity contract has an energy price of approximately $25 per megawatt hour. Now, local generation is currently necessary to do a couple things. One, it's necessary to prevent local grid overload under certain system conditions. And so what's going on here, even though this utility may have sufficient contracted resources to make it unnecessary to run their own local generation that was built some time ago, they have local grid situations where if load at a particular substation gets to a certain level, they have to have local generation online to prevent overload of that substation. And that kicks in when that substation reaches approximately 45 megawatts in load size. In the wintertime, though, they also require steam heat to heat the power plant building facilities and prevent water pipes and other parts of the facility from freezing up. And so the key issue here is what are the relative economics of the existing generation options? Should they consider retirement of these assets, or should they invest further in these older coal plants? This is a simplified schematic of their system. As you can see here, kind of in the middle, we have the 3 boilers, and the nomenclature can be a little bit confusing based on the way the facilities were constructed. The smaller boiler is referred to as boiler number 6, and then we have boiler number 7, which is the larger coal-fired boiler, and then boiler number 8 is the gas-fired boiler. We then have the turbine generators down here, which again are small, medium, and larger. These are referred to those number 5, number 7, and number 8. Number 6 turbine is part of the combustion turbine over here, which we mentioned a moment ago. And then you have the other facilities, the stacks and the condensers in the plant. So this is a basic simplified schematic of how they operate. In this particular utility, also, they can, to some degree, kind of mix and match the boilers and the turbine generators. So the steam configuration and physical attributes of the power plant does allow kind of a mixing and matching. So there's actually more potential options that we have not yet explored, where, for example, maybe it makes sense to retire one or both of the boilers, but to keep the turbine generators available for future expansions of the plant. So when we begin to frame the problem, of course, this involves gradually simplifying the problem to make it more tractable and solvable. First, what we did was we investigated the key risk and timeline issues. Obviously, if there are no uncertainties, then the solution would be to simply find the option with the lowest net present value of incremental costs. And in discussing the issue with the client, the following primary risk issues or uncertainties emerged: customer load, power market prices, fuel market prices, and capital cost uncertainty. What we also learned was that emission allowance prices and the potential severity of emission violation fines are also issues that not be considered in this version of the analysis. In terms of the issue with the fines, I just wanted to point out that this utility, of course, will always comply with the law, but the issue is a timing issue in terms of can it realistically make some of these capital investments fast enough to allow reliable operation of the plant and avoid any near-term emission fines that might tend to pop up in case they can't get the work done quite fast enough and are forced to run some of the generation above what the emission limitations would normally allow for. Again, to further simplify the problem, we've also limited the decision options to a short list for now. This list has been defined as 3 different cases. Case 1 is to invest in both units to keep them fully operational, just like they've had them in the past. So this would involve large investments to address the environmental limitations as well as the reliability requirements that the older generation needs to come up to speed on. Case 2 is to shut down the smaller coal unit but invest in the larger coal unit. And case 3 is basically what I've constructed as a hypothetical case, which would involve shutting down both coal units and then addressing the transmission constraint. Now, what we'll find out momentarily is that we do not yet have any engineering studies where we've been able to estimate the cost of alleviating the transmission and the substation constraints, nor do we know if it's even realistically feasible to do that. But the initial thought is that there might be some options to do that would be creative and that might allow avoiding capital costs at both of the coal units. In these simulation models, what I found is that almost in all cases there are some important physical or financial constraints that need to be incorporated in the analysis. And the key constraints in this problem, and we've alluded to some of them already. First of all is that in an electric utility setting, load must be served at all times. And unlike other industrial settings, there really is no flexible storage for electricity. And so what has to happen, both from an economic perspective as well as a overall grid reliability perspective, is that load and generation must be always balanced. Also in cold weather, at least one boiler, coal or gas, must operate for heat. We mentioned that earlier. And likewise, in high load conditions, which typically are in July and August for this utility, generation from at least one of the coal units is required for substation transformer support. And this happens at about 45 megawatts. And so anytime that the substation basically has 45 megawatts or greater of load, then they need to have local generation on the grid kind of on a 1-for-1 megawatt basis. And then consistent with this notion that load and generation must be in balance at all times, that energy deficits and surpluses are served from the spot market. So in cases where they have excess generation online because must-run generation required because of the constraints perhaps might be higher than their actual local load, then that excess generation is basically spilled to the spot market at the prevailing spot market prices. And likewise, if they have outages or deficits of local generation, that deficit would be served by the regional spot market. In terms of some of the model features, when I'm constructing a model like this, one of the first choices is to think about how granular do we need to make the model. And in this kind of setting, depending on the utility's generation, configuration, and the type of assets, some cases you may have great flexibility in how fast you can ramp up or ramp down the generation. In other cases, for example, a utility that's heavy in nuclear capacity, you have a lot less flexibility, again, depending on the exact technology, in changing the generation output of the power plants. In this case, what we've decided to do is reflect the model on a daily dispatch basis. So we're basically making the assumption that the utility can choose to operate its local generation on a day-by-day basis. And we then model this out for 20 years. So when you then take 365 days per year times 20 years, we end up with quite a few rows of calculations. In this case, 7,300 rows of calculations in our model. As I mentioned before, it reflects both the must-run as well as the economic dispatch of the power plant attributes. So again, we have some must-run requirements relating to cold winter temperatures as well as the substation loading constraint. And those constraints, as well as situations where the plants are actually economic to run because of market conditions, are both reflected, of course, in the model. We also want to reflect minimum output limits and associated costs. Typically, for any kind of power plant, there's a realistic economic minimum that the plant can operate at. So in the case, for example, of the 16 megawatt unit, the minimum level it can operate is approximately 8 megawatts. And similarly, for the larger units, the minimum output levels are higher as the unit size gets larger. Now, a convention I tend to use is extensive use of offset and some Excel functions. It helps me create flexibility in the spreadsheet model. One of the things I want to investigate in the future is how efficient these formulas are to use in the context of a Monte Carlo simulation. But right now I'm using these, and they seem to work pretty well again, to provide for flexibility in pointing to different columns and rows in the model, as well as aggregating results through the sum-if functions. And more specifically, in terms of the at-risk distributions, we currently have at-risk distributions defined for system and substation load, coal prices, natural gas prices, ambient temperature, as well as capital costs of capital investments. And so here's what the preliminary model looks like in terms of the input distributions. These distributions here, so for load, temperature, and energy market prices, these have been reflected for every month for each year. And so what we have here would be 12 times 1, 2, 3, 4, 5, 6, so 72 distributions for load and prices. And so what we've reflected is a different distribution for each month of the year for each of these variables. But then we've assumed that each January of each year looks the same. Otherwise, if you had actually 7,300, if you had 12 months times 20 years times 6 variables, that would be just way too many at-risk variables. So right now we're basically making the assumption that each year looks the same in terms of how the distributions play out. We, of course, do have independent between the variables themselves and each monthly set of variables. And then we also have a distribution around the capital costs. This first one is the capital cost to refurbish the 16 megawatt coal unit. And the second one here at the bottom is to refurbish the 22 megawatt coal unit. And the approximate mean costs of these investments are $10 million and about $15 million, respectively. You can also see here for load, this is again a municipal utility. So their kind of average load in this case again for January, because these variables here in this top panel reflect the load and market prices for January of each year. Average load is around 136 megawatts. We've assumed the ambient temperature again for January would be 30 degrees. Power prices are around 30 megawatts, or $30 per megawatt hour on a round-the-clock basis. So this would be the all-hours price for January. Coal prices for both units 1 and 2 of the coal units are approximately $3.60. And the natural gas prices are $3.81 for January. And I took the natural gas prices from the most recent forward price curves published on the energy exchanges. Now, what I typically do in these models is I first run them in a deterministic fashion. And what you see here in this panel is the calculated energy output by resource for year 1. And this is kind of by month. And this may be hard to see over the webcast. Hopefully you can see the screen. The gold color here is this represents the energy from the 66 megawatt contract. The purple or dark blue, this is the 70 megawatt contract. What you notice here is you don't see any output from the 16 megawatt unit. So, and this ties back with the concept of Jensen's inequality. In a deterministic setting, we don't currently, or it currently does not appear that the 16 megawatt unit is economical at all to run during any portion of the year. We do have generation coming out of the 22 megawatt unit. What's going on here is you can see the must-run generation in the winter, and then in the summer to take into account the constraints for both heating as well as the substation load constraint in the summertime. And then lastly, you don't currently see any generation out of the gas unit. And what's going on here is that the prevailing power prices are low enough and the prevailing fuel prices are high enough that it does not appear to be economic to run the small coal unit or the gas unit based on those current prices. Now, what I've also done, I do a variety of what-if analyses in the deterministic model just to kind of explore how the model works and make sure it's giving reasonable results. What I've done here in this scenario is, again, this is case 1 where I have all the generation available. But what I've done is change the gas adder, and this gas adder basically reflects the price of transportation of the gas to the local system of $1.50 per unit. And the current model, the current base case model includes a $1.50 adder for natural gas. If I change that to 0 in the base case model, you can see in the summertime, it's kind of the green color, you begin having some natural gas generation begin to appear in the model. And this is where the power prices are high enough and the gas prices are low enough to make it economical to run that gas-fired power plant. Now, when I run the simulation, what I've been doing is running the simulation with 1,000 simulations. And again, this is a 20-year model with daily dispatch. So there's quite a few calculations, and it takes approximately just over 5 minutes to run the simulation with 1,000 iterations. And again, I mentioned earlier, one of the pieces of future work would be to explore ways to speed up the simulation. But what we see here is the distribution of cost for the base case. And so what you see here is a mean value of approximately $337 million, and this is the NPV over 30 years, or excuse me, 20 years, as well as the range of outcomes at different probability levels. So this is the standard output you get from running at risk. So the mean value is $337 million. The mode also is approximately $337 million based on the actual simulation results. And so what's interesting here is that even though the distributions have been defined predominantly with log normal distributions, which tend to be skewed slightly to the right, the actual results look very close to just a basic normal curve. And the reason for this is that there's offsetting variables in here. So as power prices go up, that ends up creating higher and higher cost when they're short of energy. But in many hours, they have surplus energy because of the must-run requirements, and the system actually benefits from higher power prices when they have excess generation available. And so what happens is that even though each individual price distribution may be skewed to the right, prices tend to behave in a log normal way. The net effect economically is that we see a non-skewed distribution for the results, which was an interesting observation for me. I did not expect that. I expected there to be a positive upward skew to the cost results for the model. And we'll get into more detail on the actual comparison of results shortly. What I want to do now, though, is switch to the actual Excel model to show you how it's been structured. So what I've done here, just for sake of making the model run a little bit faster, is I've truncated the model to just 3 years of results, and basically made each successive year after year 3 equal the prior year. And so that'll allow me to run the model more quickly and have it be more responsive in live setting here. But I just wanted to step through each of these tabs in the model to show you how I've chosen to construct the model. This first tab is where we have the price forecast information. And so what I typically do is organize this information by month, by time bucket, and then years to keep track of which month and which year I'm pointing to. What we see here are the forecasted values for load, ambient temperature, power prices, the coal prices, and then natural gas. What I also tend to do in these models is I have a separate range of cells where I specify the volatility of each of these parameters. And these volatilities are based on historical observation. They're not precisely defined based on actual calculations of historical values. But generally what we've seen relevant is that you have maybe around 10 or 15% uncertainty in load, a little bit slightly lower uncertainty for prevailing temperature, relatively high uncertainty or volatility for power prices, relatively lower uncertainty for coal prices. They just don't tend to change nearly as much as other energy prices. And then again, a higher volatility for natural gas prices. And this is typical of most energy price analyses that I've seen over the course of my career. And again, these numbers can vary depending on the time horizon that we're looking at. What I then do is combine this information on this sheet over onto the simulated prices sheet. And here's where basically what I'm doing is pointing back to my forward price sheet to grab in each of the risk log normal functions the forward price I've used. Excuse me, that basically is what I'm pointing to it. And then I point for the standard deviation to the product of that forward price times the volatility input to come up with the standard deviation to use in the risk log normal function. And then for each of these simulated prices here, what I also do is include an adder that may be relevant for each price. So even though I have the raw natural gas commodity prices on my forward price tab, for example, the actual delivered natural gas prices to the utility have to be inflated by $1.50 to reflect the transportation costs of natural gas to the utility. Now, for both load and power, and this is very important in an electric utility setting, there's a daily average and a daily peak ratio that applies to both loaded prices. So what I've done here is said that each day of the week for each month has a certain load pattern, and for sake of simplicity, I've just made them kind of the same for each month. They're really not the same. They can be spikier during the summer, for example. But it reflects that the weekends, Sunday and Saturday, tend to have a lower load than the weekdays. I just normalize this matrix here and then use that for later calculations. Then I'm also estimating the peak to average load ratio for each day of the week for each month. And this allows me to basically compute the peak load as a function of the probabilistic average load that the Monte Carlo simulation produces. Similarly with load, we also have the same construct for prices. So in the power markets, you not only have day-by-day and hour-by-hour differences in load, but you also have hour-by-hour differences as well as day-by-day differences in the power prices. So just like the load, I also am using some ratios here to reflect the shape of the power prices both on an average daily as well as a peak day basis. We then have our capital costs. Here is the approximate $10 million cost to refurbish the 16 megawatt unit. Here's our $15 million to refurbish the 22 megawatt unit, or 22 megawatt unit. And then I put 10% uncertainty around those capital costs for sake of exploring the behavior of the results. I'm going to jump over here to the system data. So this is where we're putting in some of the key constraints and other economic parameters of the system. So we've assumed that their retail price is $0. The reason I'm assuming this is that in this analysis, we're trying to estimate the revenue requirement for the utilities. So we basically assume that they initially don't receive any revenue from their retail load, and the essence of the calculation is to ultimately figure out what is the price to their customers need to be for them to recover all of their revenue requirements as a nonprofit governmental agency. We assume that the substation in question is 20% of the overall system load. Here's where we introduce the 45 megawatt threshold where they have to have local generation. This is the temperature threshold where they have to have units online to keep the plant warm in the wintertime. And then we have here, by each resource, some of the economic parameters. So the capital cost per day of each unit, if there was a separate capital cost in addition to those capital investments we talked about earlier. Startup cost to start up each unit, the min and max operating ranges of each resource. This column here points to the fuel types. So for example, fuel type 4 is coal 1, fuel type 5 is coal 2, and fuel type 6 is the natural gas. And then we have the heat rates, which basically is the efficiency of the unit. The higher the heat rate is, it means it's a less efficient unit because greater heat in the way of fuel has to be run through the plant to produce electricity. What we also hear are additional non-fuel variable costs to run each plant or each resource. And then we also include a dispatch threshold. So because of the fact that each plant has to incur startup costs, what we're doing is saying the plant has to produce at least $3 of profit on a megawatt hour basis for it to make it economical to even run the plant. And so that's a simplified way of incorporating the day-by-day startup costs in the computation. And then we also have some of the additional minimum load non-fuel run costs of each plant. You have things like water costs and so forth that are also required for the plant to operate. In terms of dispatch, this is where we have all the computations, and I just wanted to kind of go by these. We have each time bucket here. We point to each day and time. And the reason this is important is that some of these models can get down to the hour-by-hour computation. We want to make sure we're reflecting the right time frame during the day when we look at the results. Here we have our market system and other variables, so load, temperature, and power and fuel prices. Here's where we're calculating the daily average load, and as you can see here, when we have just the monthly averages, we have a static value, but when we take into account the load shape information, we have a varying average daily load. And what's going on here is this is a Thursday, This is a Friday, this is a Saturday, this is a Sunday, and we get back to Monday, Tuesday, Wednesday, Thursday, Friday of each week. This number here is based on the substation percent of load. We then calculate the actual dispatch prices of each resource based on the fuel price and the heat rate. That's what's going on here. We model whether or not each unit is available. So if we're running a scenario where we want to turn off the availability of a given plant, in this case the small plant, we can put 0 in there, and it will not be available to run. Here's where we actually have the dispatch price variables, which is the price at which it's economical, which is the market price at which it's economical to run each plant. So what this means is that power prices have to be at least $61.60 per unit to make it economical to run the smallest coal unit, $58 to run the larger coal unit, and so forth. Now, what you see here is the effective dispatch price of the baseload contracts, and these are pretty attractive contracts where they're economical as long as power prices are at least $15 and $25 respectively. What we're then doing is determining whether each unit is either forced to run or it's economical to run. And we use this with basically binary math. And what you see here is, generally speaking, in the wintertime or in the summertime, it's most economical to run the slightly larger coal plant than the small coal unit, or the natural gas plant. Now, what you'll notice is that the marginal cost of the gas plant is actually a little bit lower, but because it has a higher minimum output, it's actually more expensive in total to keep the natural gas plant running at its minimum than to keep the larger coal unit operating at its minimum. We then look at if each unit is actually economical to run. What you notice here is that none of the units are technically economical to run in the wintertime, but you do have the medium-sized coal plant over here in the power column that's actually being forced to run to provide heat for the power plant. And then here's where we have the aggregation of all the parameters in terms of generation output, fuel consumption, generation fuel cost, generation variable O&M cost, so that would be the non-fuel variable cost of running the generation, total cost, total megawatt hours of energy output, as well as total fuel input across all the plants. And then we look at the total amount of spot sales net. So in this case, what's going on is that the plant has excess generation because of the large baseload contracts and the relatively lower load during this time of the year. We have an off-system positive spot sales revenue. This is where the retail revenue is assumed to be 0 because we're calculating revenue requirements, and we've assumed the retail price is 0. We have total margin when we include all that, and we incorporate the capital costs. We then have basically $80,000 of net revenue requirement for that particular day. Now, what you'll notice here on the capital cost tab is we've assumed the capital costs, if they incur them, kick in at the beginning of 2016. And that's why the capital costs at the beginning of 2015 are 0. They, of course, then change, and they materialize at the beginning of 2016 right here. When I aggregate all these data again, here's where we're using the SUMIF function. I tend to find that to be a convenient function to use in Excel. makes it a lot easier to expand and contract the model. We have all the year-by-year values, so the total megawatt hours of load, the total retail revenue, total megawatt hours for each of the generating units, total fuel costs, and so forth. And then we ultimately work our way over to the total system cost as well as the net present value of the costs of operating the system, which this base case deterministically has calculated $337 million. So this is the base case deterministic model. What I'll do is I'm going to go ahead and start the simulation just to show you kind of how it runs. And in this case, like I said, I've truncated the model to make it run faster. And I also have, I'm also running only 100 simulations to make it run relatively quickly. Okay. So now, there's a lot of great features in at-risk, but what I tend to do is after I run the simulation, I'll automatically produce some of the inputs and outputs. I'll also then browse through the results to look at them in more detail. So what I'm going to do is start with the NPV value. So here's basically the NPV of total cost. And again, the mean here is approximately, in this case, when the simulation ran, $338.6 million. We then have, of course, the full range of results over here on the right. And they range from about $272 million to about $392 million. So even though it's not a highly skewed distribution, there is a significant amount of uncertainty in terms of what their total cost will be over those 20 years. Now, what's also interesting is that in the deterministic model, we had indicated before that the small coal unit is not likely to run at all, and the gas unit is not likely to run at all based on the prevailing economics. And indeed, from a deterministic perspective, the calculated output of both the small coal unit and the gas unit is actually 0. But when we run this in a Monte Carlo setting, what we see here is that even though the most likely outcome for the small coal unit is in fact 0, you have a lot of combinations of scenarios where you do begin to get significant generation out of that plant. So these are cases where it is actually economic to have that plant. The question is, how economic is it in the scheme of those large capital investments that would be required for the plant to still be available? Here we see the generation out of the 22 megawatt unit. It's much more evenly distributed, and what we're seeing here is the impact of the must-run cases in the winter and the summertime to make to satisfy the system constraints for temperature and substation load. And then, like the smaller coal plant, the most likely outcome to the natural gas plant is still 0, but we see an even larger amount of potential generation out of the natural gas plant. And so again, you could have scenarios where, depending on how volatile prices are, you may have very economic conditions, and that makes having that gas unit attractive. And then back to our total cost of NPV. So these are the base case results. What I'm now going to do is flip back to the PowerPoint deck. And compare the results. So again, this is the scenario of investing in both coal units. We see the mean value of approximately $338 million. And we can see the range here, ranging from $257 million up to about $381 million at the extremes of the distribution. Now, case 2, we ran the same model where what we basically did was we removed the $10 million capital cost from the model because we're going to retire and not invest in the coal unit. We'll go ahead and invest in the newer coal units. And what you see here is our mean cost has gone down, to $329 million. And then in the hypothetical case, if we retire both coal units, we drop down to an expected cost of $316 million. If we put those all in the same graphic, we get this summary. So the most cost savings occurs by hypothetically retiring both coal units. But if we go ahead and simply retire the small coal unit, we also do save about $9.2 million. Now, what I've also pointed out on this slide is the P5 and the P95 ends of the distribution, which is the 5% and the 95% ends of the distribution. And then I've also looked at the difference between the P95 and the mean. And sometimes I'll go ahead and do this calculation to look at how skewed the distribution is and whether or not there's a difference in the amount of skew between the different cases. And like we alluded to earlier, the actual behavior of their system is not very skewed. And by changing the combination of the generation assets, it doesn't alter that. And so, for example, in some cases you might see by retiring one or both units, you might have a better mean cost. In other words, it's advantageous to retire one or both units, but you could have a P95 cost that is slightly higher, meaning that you have a greater amount of risk in those cases. But that is not the case we see in this particular utility system. So sharing some observations with you. First of all, clearly the system economics of this model are heavily dominated by the baseload capacity contracts. And the 70 megawatt contract is heavily in the money. What I'm going to do is flip back up to that slide real quick here to show you that behavior. What's going on here is this 70 megawatt contract is priced at $15 per megawatt hour when their own local generation is between $50 and $60 per megawatt hour to run. And so these contracts, in particular the 70 megawatt contract, heavily dominates the economics of the system. But there's still significant uncertainty based on the prevailing power, fuel, and load values. The presence or absence of one or both coal units does not appear to be a major driver of system costs. And so the point here is that by removing one or both units, it doesn't really change the system dispatch a whole lot. But the key issue is really how much and where do we invest? So do we really need the coal units to support the system constraints at the substation? Now, a key factor here in their system is that the gas unit is tied into a different point on their grid, and so the summer constraint for the substation is not alleviated by running the gas unit. It's only alleviated by running one or both of the coal units. What we see here is the best option may be to retire both coal units, and we do not yet know if the substation or transmission reconfiguration is realistic or how much it would cost. This particular company has done very extensive power plant condition assessments and environmental cost estimates to refurbish the coal units. It has not yet, to my knowledge, looked extensively at reconfiguring the substation or other aspects of the transmission to alleviate the 45 megawatt transmission constraint. But it appears that would be an option if the cost of it is less than $22 million. And where I get that is based on this delta here. So this is the cost savings of retiring both coal units that is estimated. But currently, that would not be practicable because you have to have at least one of the coal units to solve the summertime substation constraints. This just indicates that you have approximately $22 million of headroom that you could potentially spend on alleviating that constraint at an approximate level. But further study of that is, of course, needed. In terms of next steps, what we expect to do in terms of anticipated model refinements, we want to incorporate emission rates, costs, and limits, as well as incorporating scheduled and forced outages. Most utilities will have scheduled outages of especially their fossil-fueled units. And you also have key issues relating to the potential for forced outages. And when we incorporate those variables, our expectation is that keeping 2 units for redundancy may be very valuable. We also need to estimate the cost of addressing the transmission constraint and incorporate that into the model. We also want to refine the load and fuel price term structure. As I mentioned before, we've assumed that each future year looks the same as the first year, even though the month-by-month values are changing in the Monte Carlo simulation. And we anticipate making use of the time series features and at-risk to do that. And then lastly, we want to include some capital financing logic to reflect the bonds that would be issued and the interest payments that would be issued or that would be made to finance these capital investments, and then also to explore some model speed-ups. So some concluding thoughts here is that definitely businesses that tend to benefit from simulation modeling have one or more of the following characteristics. They have some degree of flexibility or optionality. They have operational or financial characteristics that are nonlinear or asymmetric. Now, again, one of the learnings in this particular case study is that even though they have nonlinear inputs in terms of the load and the market price inputs, the actual results of their system economics are not very nonlinear. They appear to be kind of normally distributed, even though there still is significant uncertainty in the costs of the future costs of the utility. And that implies that there may be hedging strategies that will continue to be attractive for them to lock in attractive costs as they arise in the marketplace. Other key issues is that when you have positively or negatively correlated prices or other variables, those are all, that also would be a situation where Monte Carlo simulation ends up being very valuable and will produce different results than a deterministic model. And so the application in this case is that typically what we see in today's energy market is that there's a very strong correlation, depending on the time period, between natural gas prices and power prices. And that's another refinement we want to make in this model to explore what is the effective correlation between those prices and whether or not that changes the differences between the deterministic and the probabilistic results from the model. And we continue to believe that arguably Monte Carlo analysis is not just an interesting technique, but is actually necessary to produce high-quality business valuation and assessment results when you have the above characteristics in play. And again, we find that most businesses do in fact have these characteristics, and that the return on an investment of implementing simulation tools such as DecisionTools Suite can be very high. The challenge, though, is how do you make this switch? How do you incorporate and introduce Monte Carlo analysis in a corporate setting? And in my experience over quite a few years, there are some interesting dynamics that occur in a corporate setting when you begin introducing these techniques. And what I'm doing here with this graphic to the right is paying homage to Maslow. Hopefully, most of you recognize this as what's referred to as Maslow's hierarchy of needs. But invariably, what I found is that even though we're dealing with technical topics in the introduction of simulation techniques, the human factor and corporate culture ends up having a big impact on the ability to introduce these analytics. And basically, it all revolves around, gee, that's not how we've done it in the past, which is, I find, pretty interesting. And some of the key issues that you need to understand will tend to happen is that when you introduce Monte Carlo simulation, you produce different results than with deterministic modeling. Now, even though the simulation results can be argued as being more robust The problem from a corporate perspective is that, number one, you don't want to declare that the previously used deterministic models are incorrect, because very large investments of both human effort and financial resources have been made in the traditional deterministic models. So first and foremost, I would recommend people avoid declaring deterministic models as incorrect. They're not incorrect, they're just incomplete, depending on the nature of the business problem being analyzed. And so it's important to know, though, that others may feel threatened. They've invested significantly in those deterministic models, and it's important to respect that. Because of that, it's really important to be prepared for pushback. In many cases, companies may say, well, we've never done it this way. And in a more severe case, we've seen examples where companies became concerned because the Monte Carlo analysis implied that they had made prior decisions that were questionable. So that has to be handled in a very delicate way. And then invariably, depending on who the audience is, Monte Carlo simulation can be a little bit daunting in terms of understanding it, and that can lead to some pushback in terms of introducing this technique. Another thing to keep in mind is that in most cases, it's really unnecessary and it's practically impossible to perfect the distributions used. And what I'm referring to here is that invariably you'll find yourself in discussions on, what really does the historical data look like? How do we determine our probability distributions? And from my experience, what I found is that it's more important to get them approximately right and to reflect a full complement of uncertainties rather than to perfect each distribution. So said differently, it's more important to reflect the full range of different uncertain variables in an approximate fashion than to pinpoint any single distribution. It's also very important to make sure physical constraints are incorporated. An example of this would be a capacity-limited business problem. So, for example, you may have a manufacturing facility, or let's imagine, for example, a restaurant that is looking at the growth of its customers and its revenues. Because of the fact that you have a cap on the amount of customers you can serve, those kinds of constraints must be reflected in the model, otherwise you can get unrealistic results when you apply the Monte Carlo analysis. I recommend starting with simple examples to illustrate how the simulation model works, and then of course be helpful and persistent as these techniques are being introduced. Positive communication and focus on teamwork and joint problem solving and improvement opportunities is really key. In terms of some further study, in the prior two webcasts, we provided some references that I found to be very valuable. The four remaining of these in my top 10 that I think are relevant are not only technical references in terms of Michael Porter's competitive advantage. This is the companion to competitive strategy, which I think is really the most informative and most complete treatment of what competitive advantage and competitive strategy consists of. Competing on Analytics is a very interesting book that talks about how leading analytics have been applied in increasingly strategic ways by modern corporations and making use of large data. And then from a managerial perspective, I found that Primal Leadership, which is a book related to the text Emotional Intelligence, and then lastly the classic 7 Habits of Highly Effective People. These are, of course, not technical texts, but I found them to be very valuable to think about how to improve effectiveness in organizations and how to think about the dynamics of teams depending on how experienced the personnel is, as well as what corporate culture might be in these settings. So with that, we'd like to conclude. We have run over by a few minutes, so I appreciate your patience and participation. And now I'd like to open the webcast up for any questions that any of you may have. So Jameson, do you want to take it from here?
Yes, certainly. Thank you so much, Glenn. This was great. We do have a few questions if you have time. One came in. This is interesting. An alternative that was not considered was an all-new generation unit, which might be better environmentally and better in the distant future. Is this alternative unreasonably expensive? Any comments about that kind of scenario?
Yes, that would absolutely be a good alternative to consider. The basic challenge in this case is that because of these baseload contracts, the utility already has, you know, in some periods of time, more generation than it needs. And so it really doesn't make a lot of sense necessarily for the utility to explore additional generation in the future. But certainly if those contracts were to expire and the utility would need additional local capacity later, it would be very feasible and important to evaluate whether to add additional environmentally attractive generation or to maybe extend or to renew those contracts if that was possible. So absolutely those would be important alternatives to consider in the future.
That makes sense. Let's see, do we have another question? Oh, wait just a minute. We don't want to keep you too long, but I thought that that occurred to me too. I was thinking about that. In fact, we were having a coal versus gas discussion while I was muted while this was and the implications of that. And let's see. Well, I don't have any other questions coming in except for just kudos and thank yous. Let's see. We'll give it one. We'll give it. Is it okay if they email you a question if it comes up later, or if you're watching this webcast in the future?
Absolutely. I'd be happy to interact with anybody that has questions, and we are, of course, available to help anyone interested in building models or exploring how to improve their existing models. So we'd love to have that interaction. And also, I just wanted to reemphasize that we'll be covering this at the annual conference in November, and there's quite a bit more detail that we expect to have at that point, as well as to be able to cover in a little bit more depth some of the inner workings of this particular model, as well as the simulation performance itself.
That's good. Good. Thanks for. Oh, one more thing. What can you say? Have you studied the volatility aspect of this project, and how would you address some of that?
Sure. We have not explored that yet. We just haven't had time yet. We've been really focused more on the operational parameters of the physical system. But one of the things I alluded to earlier is we certainly recognize that we probably need to treat the term structure of volatility in a more realistic way. And this deals in part with the important distinctions between spot prices and forward prices for these commodities. The volatility representation we have at this point is not particularly sophisticated. What we don't know is how much it really matters. So that is an area where we'll want to explore is number one, determining really what the proper volatility inputs should look like, but then determining, well, how much does it really matter? In some cases, the representation of volatility ends up making a big difference. In other cases, it's not exactly how you represent it, but more a case of, are you including volatility? Mm-hmm. And so that can be a dynamic we'll explore later.
Well, we really want to thank you, Glenn. This was great, and thank you for going to New Orleans too. And
I'm looking forward to it. I appreciate the invitation.
Hopefully, we'll see some of you there in New Orleans too in November. And if you have any questions about the webcast or even the conference, feel free to email me. And any questions for Glenn, email him anytime. And I'd like to thank everybody for joining us today.
Thanks very much, Jameson, and we'll be talking with you soon.
Yeah. Sounds good. Thank you, everybody.
Have a good day. Goodbye.
Yeah.